Hello everyone. For those of you who don't know me yet, my name is Hanna Diewald, Chief Editor of MAFO, Ophthalmic Labs and Industry. The following video is the second part of MAFO's new video series MAFO Talks. The new format features technical presentations for the ophthalmic optics industry, followed by enlightening Q&A sessions. Today, Professor Jalie will present his speech on an easy method to measure the back vertex power. Afterwards, you will see the Q&A with Peter Baumbach, who will discuss the lecture, but also further questions with Mo. For example, the consideration of high-order aberrations in spectacle lenses. Are they a waste of time or a real enhancement? Stay curious and please enjoy watching.
Hello everybody. I am delighted to be able to address you again with a short talk on the accurate prediction of back vertex power. You will know that I try to find an educational topic which is of interest to colleagues on the manufacturing side of our profession, and I hope that you find this year's topic to be of interest, with the arrival of spectacle lenses being manufactured in 1/100th diopter steps instead of the usual quarter diopter intervals. Two things have happened in the last few years which have brought about the necessity to be able to produce lenses with this degree of accuracy. Firstly, freeform manufacturing, which has enabled the laboratory to eliminate the requirement for tool ranges for smoothing and polishing the surfaces. Generally, a different set of tools is required for each different material that the laboratory chooses to manufacture. Secondly, the introduction of new sight testing equipment which can measure both the prescription and the higher order aberrations of the eye to 1/100th of a diopter. Several manufacturers allow eye care practitioners to order prescriptions in 1/500th of a diopter intervals. As a result, I am often asked by colleagues in optical laboratories for a simple method to measure the back vertex power of a spectacle lens with an accuracy greater than that provided by their photometers, so that, for example, they can check the accuracy of their automatic lens meters. If you have access to an accurate sphygmometer which can measure either the surface power to an accuracy of 1/100th of a diopter or the surface sagittar or sag to 1/100th of a millimeter, and lens thickness calipers, both of which should be found in every laboratory, then the simplest method is to measure the powers of each surface, followed by the axial thickness, and to calculate the back vertex power from a knowledge of just these three items and the refractive index of the lens material. Modern forms of sphygmometers are calibrated directly in surface powers for a given refractive indices. If the instrument records the sag of the surface Z, then it can be converted to the surface power F by means of the surface power formula F equals 2000 n-1 times Z divided by y squared plus Z squared, where n is the refractive index of the lens material and y is the distance from the centre leg to the touching point on either leg with the surface. When the front surface power F1 and the back surface power F2 are known, and the actual thickness TC has been measured with thickness calipers, the back vertex power of the lens can be found from back vertex power, or BVP, is equal to 1000 divided by 1000 divided by the front surface power minus the center thickness TC divided by the refractive index N, to which is added the back surface power F2. By way of an example, a sphygmometer calibrated for surface powers on CR39 material, whose refractive index is 1.498, reads plus 8.8 on the convex side and minus 4 on the concave side of a lens whose actual thickness is 3.8 millimeters. What is the back vertex power of the lens? Substituting into the formula which gives the back vertex power, we find the BVP equals 1000 divided by 1000 divided by plus 8.8 minus 3.8 divided by 1.498 plus minus 4 equals plus 9 minus 4 equals plus 5. You will note that I have written out the formula for the back vertex power in the simplest form for direct calculation with a pocket calculator when entered in the following manner. The sequence of steps on the calculator is as follows. Enter 1000 into the calculator. Press divide. Enter the front surface power plus 8.8. Press minus. Enter the actual thickness in millimeters. Press divide. Enter the refractive index. Press equals. Enter 1000. Press divide. Press answer. Press equals. Enter plus. Enter the back surface power. Press equals. The display now shows the back vertex power. For those of you who have not used the calculator for many years, the calculation really is as simple as that. Thank you very much for listening to me again.
Thanks again. I'd like to welcome you today to our second session of MAFO Talks in this digital format. And we heard a very interesting lecture by Mo about the measurement of the back vertex power. And therefore, today we would like to ask you some further questions, Mo. And I'd like to hand over to Peter Baumbach, our long-lasting chairman, who will ask you the questions.
Thank you.
Yeah, thank you, Hannah. Dear Mo, first of all, I would like to thank you for your excellent presentation about a simple measurement of back vertex power. And as always, in the last years of the MAFO conference, your presentation came across very clearly and precisely. And I have to say this, I wish we had more professors like you here in Germany. So I thank you really very much for this presentation. My first question is, you mentioned it shortly, but what can we do practically if the sphygmometer is calibrated directly to surface power and the refractive index does not match that of the given lens material?
That's a very good question, Peter. Fortunately, with modern electronics, most sagometers convert themselves in that you can enter the refractive index that the material of the lens has been made, and it will automatically give the correct surface power. But if it is a fixed refractive index, then you would have to convert the reading using the surface power formula, and then the one that I have given you.
Mm-hmm.
So you can manipulate the formula that's in the slides so that you can change the refractive index. That's a fairly simple operation that I guess most labs will already be familiar with, because certainly in the past they had to do this calculation when they only had a set of tools, for example, to work on crown glass or on CR39, and then we had many new materials arrived, and so with their one set of tools they would have to alter the change to find the correct surface power.
Mm-hmm.
The formula is very simple. It's simply surface power equals 1000 times n minus 1 divided by the radius in millimeters.
Mm-hmm.
So they can use that formula to find use first of all the formula I've given you, connecting the surface power with the sag, and then the refractive index formula, the tool power formula, to do the conversion.
Okay. I was asking this question because I think that in every laboratory, these old ones are present, and I don't know how familiar they are with the electronic ones. So that was the background of my question.
Fine. Yes, it is a really good question. My advice would be to invest in a new sagometer where you can switch the refractive index. They have been on the market now for at least 10 years.
Mm.
So a lab that's equipping itself, certainly if they've equipped themselves with free-form machinery, the cost of the sagometer is tiny compared with that enormous expense.
Yeah. Mo, I have another question. Most powers today are minus powers. And is there still some mathematical leeway for any further simplification of your formula for this range of powers?
For minus only?
Yeah, for minus only.
Do you mean for surfacing the back curve, or do you mean the whole lens is minus?
And my question is it possible to further simplify this formula if the thickness doesn't play a significant role?
If the thickness doesn't play a significant role, then the power is simply the sum of the two surface powers. But every real lens, of course, has a thickness. And that thickness, when we're trying to find an accuracy to 100th of a diopter, then the difference is apparent. So for high accuracy, you should use the formula as I've given it.
Okay, because in some books, they say this is a possible simplification if to calculate the power of the lens, if the so-called Eigenvergrößerung is almost 1. But we are talking here about such an accuracy that it's not possible.
That is correct.
Mm-hmm. And the accuracy brings me to my third question. You also mentioned that nowadays the eyes are analyzed very precisely with for example, the Eye Profiler Plus or the DNI Scanner Pro and so on. And low and high order aberrations are measured, and the refraction values are sometimes specified in hundreds of an diopter. So what do you think of these methods, especially in light of the fact that the eye is a living organ and the brain may interpret same things differently at different times?
Indeed. Again, a very deep question, because one can argue that the eye has a depth of focus of at least a quarter of a diopter on either side. It depends on the pupil size, but and the other comment, I think trying to introduce higher order aberrations is really a waste of time for a spectacle lens, because every time the eye blinks, it sweeps another tear lens in front of the cornea. That tear lens cannot be the same for each sweep of the eye. And so what I'm saying is that the higher order aberrations of the eye change every time we blink. Whereas once you've made a lens, you can't change that lens, that spectacle lens. Mm-hmm. And so I think it is, we used to make lenses in quarter diopter steps because we were limited by the tools that we needed to smooth and polish the surfaces. That restriction has gone. And because of that, there is no reason why we shouldn't seek to find the best power at the time of the refraction, accepting that that might change during the day. There might be a diurnal change. Mm-hmm. It was interesting, but because of my curiosity about whether it really worked, I had my eyes tested by a DNI machine from Rodenstock, and I could tell the difference between 012 and 09. I preferred the 09, and Rodenstock were kind enough to make me a pair of spectacles, and I'm very happy with them. But I cannot say that I would have not been as happy if I'd had them correct to the nearest 025. Mm-hmm. So not enough testing has been done as to whether there is really much comfort, more comfort, by prescribing in 100th diopter steps. Mm-hmm. However, having said that, from the patient's point of view, from the client's point of view, for them to believe that they've had spectacles made to measure for them individually, correct to 100th of a diopter, whether it's necessary or not, I think that is important for the profession to keep in mind.
Mm-hmm. Yeah, thank you very much, Mo.
Thanks a lot, Mo. That was very interesting. Yeah, thank you, Peter, for asking the questions.
Thank you, Anna. Goodbye.
Okay.
Goodbye. Bye-bye.